So, welcome to Corona Chronicles. I know 6.0, 7.0, completely lost track of whatever day it is these days. And I am going to talk to you today about spontaneity, and I just want to take 2 seconds and just say hi because I miss you all. So, and I hope everyone's doing well. I just want to make sure as we get the stream started today that a few things are just, good. I want to make sure that you can hear me, so give me the thumbs up on the side. You can hear me. Make sure that there is no echo because I'm slowly starting to learn that I need to mute my speakers before I begin. So just give me the thumbs up that you're not hearing an echo and that you can see what's going on. Just give me thumbs up to let me know that you're here and just say hi so I know you're here. So give me the thumbs up you are right now watching. So just say hi. There is no echo because I'm slowly starting to learn that I need to mute my speakers before I begin. So just give me the thumbs up that you're not hearing an echo and that you can see what's going on. Just give me thumbs up to let me know that you're here and just say hi so I know you're here. So give me the thumbs up you are right now watching. So there is an echo. Okay, is it the echo where you hear my voice over and over and over again, or is it just an echo, like a small echo? And that you can see what's going on. Just give me thumbs up to let me know that you're here and just say hi so I know you're here. So give me the thumbs up you were right. I think I took care of it. Let me know if that's okay. There's a 30-second delay, so just give me the affirmative from this moment that you are not hearing an echo. And I'm going to apologize in advance. I drank a cup of coffee like literally 2 seconds ago, and I like didn't go down the right pipe, so I'm coughing. I'm not dying, I swear. All right, just give me the thumbs up that I fixed the echo problem. There is still an echo. Or Harrison, you're giving me the thumbs up that we're good. Okay. Okay, I think the thumbs up means that there's no echo. So just tell me yes. Tell me no, there is no echo, or yes, there is still an echo, because otherwise I'm going to start. Okay, good. All right. So here we go. We're going to talk today about something called spontaneity. And, if I looked up the definition, and then I went to Google and I Googled spontaneity, and I looked at a whole bunch of different images. And this image came up and it said spontaneity is to be spontaneous. So today we need to talk about, well, what does that actually mean? It's like defining, like saying the sky is blue because the sky is blue. We actually have to have a conversation. Well, what does it actually mean to be spontaneous? So I went down a rabbit hole and I started looking at all of these different inspirational quotes that I found on on the internet when I Googled spontaneity, and these are all the different things that came up. So I'm going to give you like a minute. I want you to read them over. Some of them are definitely more applicable to science. Some of them are just kind of more applicable to your real life. I want you to read all of these different quotes, and I want you to come up with, what does it mean to be spontaneous in your everyday life? So take a minute, start reading through them, and on the side chat bar, just kind of give me your working definition. There doesn't have to be science answers at this moment. I just want to know, when you read these things, how would you define spontaneity? Take a minute, read them over. I'd say talk amongst yourselves, but it's not really talking, it's more typing. Start typing in what you think this word means to you. Don't give me a science definition yet. Just look at these words and tell me what's coming to your mind. Go. Olivia, I like what you're saying, to take action. It's a great one. Okay, there should be some more responses here. Keep reading. And it doesn't have to be right or wrong. Just give me a couple of things that are coming to your mind. Crazy. Oh, I like that one. Mason, what do you mean by crazy? Like, explain that to me. What does that mean? Being original, like that one. Yeah, Mason, go ahead. Call Johnny out. Talini, any thoughts? You got anything you want to share with us? Is he actually here? Is that kid around? Johnny. I'm checking the chat bar right now. Is Johnny alive? Is he here? Okay, so kind of like an out of control action or reaction. Like in that. Okay. I don't see Johnny here, Mason. Okay, Taylor, I like that one. Different. Okay, so I'm looking at the side chat bar right now, and I'm looking at some things that that people are saying, and some of these things can be related to chemistry. Some of them could be tied to chemistry in a more indirect pathway. But overall, I'm loving what I'm seeing, because I think the word spontaneous is a little bit different than what you normally would think in your everyday life compared to how we would talk about it in chemistry. So I'm looking at the chat bar. Olivia says to take action. Mason says crazy. Dylan says being original. And then Mason wants to know what Johnny thinks. Jordana says kind of like an out of control action or a reaction, and Taylor says something that's different. I can see how all of these different words have different context, and they're the same word, but different context in your everyday life. So we need to talk about what does it actually mean in order to be spontaneous in science, and that's a little bit different than what the word spontaneous means in your everyday life. Not to say that your connections to everyday life are not going to be useful, but at the same time, I feel like this word has different context appropriateness in different situations. We're going to come back to this little inspirational quote wall in a few minutes. I want to head to the next slide with you, because we got to talk about what it means to be a spontaneous process in science, because there's definitely a difference in how the context a scientist would use this as opposed to what the context would be in your everyday life. When we talk about it in a scientific context, and I probably need to get rid of this, we talk about it as a process. So I'm just waiting for this to delete. We talk about a process, or a spontaneous process, as one that occurs on its own without energy input from the inside. And some examples would be, a ball will roll down a hill. Like, do you have to ask a ball to roll down a hill? Like, no matter what, in any context scientifically, if you put a ball on the top of the hill, it's going to roll down that hill, down that incline, without any extra external source of energy. The same thing with water. Like, water will always flow downhill. Like, there's no time and place where, water's not going to flow downhill unless you stop it by putting in some sort of external energy, by building a dam, or getting rocks and putting them in the way. Like, that would be some sort of external energy that you would need to invest in order to stop that from happening. A spontaneous process is something that just happens on its own without any additional input of energy from the outside. So if I go back to that little, word quote wall of everything that was going on, I just want to delete this box. I go back to this word quote wall of everything that's going on. I think that any of these quotes could kind of get at that. This whole concept of it just happens without there being an external energy source. And I'm looking at the comments that were on the sidebar, like something that is, being original. Like, if you're original, you're true to yourself, you're not changing who you are. It's a different context way of thinking it. It's not exactly how a scientist would think about it, but it is something that is original, something that's happening on its own without any sort of modifications. And that's kind of the scientific concept, something that would just happen without you asking it to happen, without there being some sort of external energy source forcing that to happen. Okay, I take a look at what Jordana says, something that is kind of out of control. Yeah, if I think about spontaneity in terms of science, you don't control it. It just happens on its own. So all of the things that I am looking at here, of all the different quotes that are definitely appropriate for everyday life, I think that some of these are just more appropriate scientifically, I am spontaneous and slightly out of control. Yeah, well, I think if you're talking to a scientist, anything that's spontaneous is by definition out of your control. It just happens on its own. This particular one, spontaneity, it's better to be spontaneous and let things happen. Well, that's what it means in science. Something that just happens on its own without you forcing it to happen. That would be something non-spontaneous, where like you are investing energy to force something to happen that never would have happened in the first place. And then the final quote that I think really hits home for me is spontaneity has a time and a place. And we're going to come back to this one because not everything in nature is spontaneous. Like, not everything just happens. In fact, there's a lot of things that do not just happen in the universe that are really, really important, like photosynthesis. Like, that doesn't just happen. Like, plants have to invest energy in order to make their own food. Like, that's what they do. And like the whole entire concept of like, you know, like life, like that's not spontaneous. We'll talk about that in a little bit from a biology perspective, but there are things in science that are not spontaneous that need to happen. They do happen, but they only happen if you have some sort of external energy source that's going to provide you with the energy that you need in order to make that happen. So, I'm just going to hit the pause button really quick, and I just want you to give me a thumbs up on the sidebar to make sure we're in a good place and you wrap your mind around the difference between spontaneous context in your everyday life versus how a scientist would use spontaneous in a scientific setting. Take a minute, give me a thumbs up, make sure we're in a good place, and then I'm going to move on. Okay. Awesome. Good, good, good. All right. So, one of the quotes that I found as I was, you know, going down my rabbit hole on Google image search was this particular quote that says spontaneity has a time and a place, because not everything in science is spontaneous. I'm going to go over here, and this is really important. Not everything is spontaneous. I'm going to go back to those examples. That's just massive. Okay. Not everything is spontaneous. And let's go back to this list for a minute of things that I had for you that were spontaneous. Like, let's go back to this list. Like a ball rolling down a hill. Like, that's spontaneous. It will always happen on its own. Like, when was the last time you saw a ball rolling up a hill? Like, have you ever seen that before? I mean, maybe like you've seen somebody like roll a ball up a hill, but what did they have to do in order to get that ball to roll up a hill? They had to invest energy. Have you ever seen water flow uphill? Sure, you can do that, but it requires some sort of pump that's going to be able to pump water up that hill. You are investing energy to make that happen. So not everything in this world is spontaneous. And then the question becomes, well, spontaneity has a time and a place. What are the conditions that you need that are going to make something spontaneous? What is the time and the place when something becomes spontaneous? And there are two criteria that a scientist is going to take a look at in order to determine spontaneity. And these two criteria are called entropy and enthalpy. They are two different criteria that have to be addressed in order to determine if something is spontaneous. So this is kind of like a flow chart. So spontaneity, and I probably could raise this. Spontaneity, I'm going to go underneath, and let's shrink you down super small. Spontaneity is determined by two things. There are two criteria or two different factors that are going to have a role in whether or not something is spontaneous, and the first one is entropy. I'm going to start off with entropy, and then I'm going to get into enthalpy. And for whatever reason, when scientists decided to get together and name this, They have like a, they named it really similar. Sometimes people, when they see these two words, they're like, this one starts with ENT and this one starts with ENT. And they're like, oh my gosh, this is so confusing. This is the most difficult thing I've ever done because these two words look so similar. They're not similar. They are two very, very different concepts. Entropy, according to a scientist, and I'm going to drag this up just so I have enough room to define everything that I want to do here. Yeah. Entropy is going to be, and my computer is just frozen for a second. You don't want to play? No? No? Yeah, okay. Entropy is defined as, and I'm going to shrink you down one more time, super small. Okay, Smart Notebook is just a moment. Really doesn't want to cooperate right now. Bold underline. Okay, so entropy is defined as, by a scientist, as the amount of chaos, randomness, and disorder in a system. And in order for you to be spontaneous, the universe, or just the way of the natural world favors more chaos and more randomness. And I'm going to tell you a couple stories about this that just, I feel like, illustrate this process. And actually, before I tell you the story, I should probably put the symbol in. So here we go. Entropy is abbreviated by chemists. We look at the change in entropy and we show that change with the symbol delta. As soon as this fires up with my writing tool, we represent that change with a delta. This is taking forever. And the symbol for entropy is S. So we represent entropy as delta S. And the natural world favors more chaos. So a positive delta S would mean more chaos, and a negative delta S would be less chaos. And I'm going to actually go back to the typing tool just because it's easier to type. And I'll define this down here for you. And we definitely shrink you down super small too. So a positive delta S means that we have more chaos, whereas a negative delta S means that we have less chaos. So let me tell you a couple true life stories about things that go on in the life of Vandercoot on a daily basis. So I wake up in the morning, and I usually wake up about 5:30 in order to get ready for the day. And that sounds kind of early, I'm sure, for you, but you got to keep in mind, like, I live about 45 minutes on a good day if there's no traffic, the weather's fine, and it's about a 45-minute drive to Belmore. And I'm technically supposed to be there at like 7:20, so like, I can do what I got to do in the morning. So I wake up at about 5:30, and at that time, like, I wake up, I roll out of bed, the first thing that I do is I make a cup of coffee, and then I I pound that cup of coffee while I make my second cup of coffee. I go and I take a shower, and I drink that cup of coffee while I'm taking a shower, and then I get out, I put on my makeup, I look around my house, and I'm like, oh, I gotta grab those papers, and I'm like, I gotta grab my computer, and I'm like, oh, I gotta make sure the lunches are packed, and the dishwasher's empty, and that the backpacks are packed, and everything's ready to go. And then I turn around, next thing I know, it's like 6:30, and I'm supposed to be at work at like 7:20. So now I'm like, oh dear Lord, I gotta go get dressed. So I run into my room and I start throwing on clothes, and I put on my first outfit, and I'm like, nah, you really don't look that great. And I take the clothes and I throw them on the floor, and then I put on my second outfit. I'm like, nah, you kind of look like a sausage. That doesn't really look that great too. And I throw those clothes on the floor, and after like 2, 3, 4 times of figuring out what I'm gonna wear, I then say, you know what? It doesn't really matter. And I run out the door, and I leave that pile of clothes on the floor, and I drive to work, usually at like 90 miles an hour down the Seafood Oyster Bay, so I can get there at 7:20 in the morning. It's usually more like 7:25. Don't tell anyone who's listening to this video who's responsible for my job, but I get there at about 7:20, 7:25. And then I have to run around and make photocopies. I have to teach you all day long. I have to grade papers. I have to answer parent emails. I have to plan lessons. I have to grade things. I gotta put things into the computer. I'm running around all day long at school. You see how chaotic and random and disordered my life is. Look at my desk in my classroom. Like, it is a hot mess. And then after all that is over, I have extra help after school. I get back in my car. I drive 40 minutes back home. It's usually longer because there's more traffic on the way home. But I get back home, and that's probably the only 40 minutes of quiet that I have in my life. But I get back home, and then I got 3 kids who need to do homework, who need to eat dinner. The dishwasher needs to be unloaded again and reloaded again, and the backpacks need to be emptied and repacked, and the lunches need to be made, and the dinner needs to be made. And then I gotta do laundry and give everyone baths and put everyone to bed. You see this? Like, this is getting very complicated and chaotic. And then all of that goes on, and I finally sit down at like 9 o'clock at night, and I can start doing what I need to do for work. And then it's about 10:30, 11 o'clock, 11:30. I go in my room and I look at that pile of clothes on the floor, and I say to myself, do I really want to put all those clothes back into my closet? Do I really want to do that right now? And the answer is, oh, heck no, it is not happening. And I go into bed, and then I wake up the next morning, and the entire cycle starts all over again. And the next day, there's more clothes on the floor. And then the next day after that, there's even more clothes on the floor. And by the time Friday comes along, this is kind of what my closet looks like. I grabbed a whole bunch of stock images. So let me grab this. This is not my closet. I wish it was my closet because it's super big, but that's not my closet. This is kind of what my closet looks like by the end of the week. So like, this is Friday. Now, I just want to ask you, over the course of the week, what is happening to the randomness and the chaos and the disorder in my closet system? I'm going to give you 2 minutes, and I want you to look at that picture and listen to my story and then tell me what's happening to the chaosness, the randomness. And then I'm going to ask you, is my closet ever going to clean itself? In order for my closet to get clean, what do I need to do? Take a minute and answer that question on the sidebar. What is happening to the chaosness and randomness of my closet over the course of the week? And what needs to happen in order for my closet to look like this? Oh, Alexa, yep, you're right. I have to clean it. Alexa, in order for me to clean my closet, what do I have to invest? I love it, Taylor. Taylor says, I need to use energy. I have to apply energy in order to clean my closet. The closet will never clean itself. And in fact, my closet is going to become more chaotic, more random over the course of the week, because ain't nobody gonna clean my closet except for me. So usually what happens, like on Friday night, on Saturday, it's not true, Friday or Saturday night, it's usually like sometime on Sunday afternoon, my kids are napping, I look at that giant pile of clothing outside of my closet. It kind of looks like this. This is actually kind of neat. It's kind of neat. And in order for me to fix this problem, I need to invest some energy in order to make this happen. So the natural way of the world, the natural organization of the world, is to head to more chaos. Like, this is favored, this is favored. That is what is going to happen over the course of the week. And my closet, I'm never going to walk into my room one day and all of a sudden my closet's like, I just organized myself. Like, that doesn't happen. Like, this does not happen naturally. You have to invest energy in order to make that happen. That doesn't mean that things do not become more organized or less chaotic. It's just that it's not natural. Like, it doesn't just happen. So my next question I want to ask you is, if more chaos is favored, I want to ask you, is the human body chaotic? I want you to take a minute and think about that for a minute. And I want you to start answering on the sidebar right now. Like, is life and the human body chaotic? Answer that. And I'm just going to get rid of let's shrink down some pictures. Shrink this down. Start answering that for me. I'm waiting for you. Is life and the human body chaotic? Okay, Audrey is saying yes, life, it's definitely chaotic. Olivia says, yep, it's definitely crazy. Alexa says, yes, it's crazy, but it has a system. And cells to take care of certain tasks. Scott says, yes, the body is chaotic. I'm going to throw something here really quick, and I just got to go on because I have two computer screens running at the same time, and I want to Google search something for you. I want to show you this picture. This is the basic, what we call functional unit. This is what we call the basic functional unit of life. And I'm sure you've seen this before because you all took the living environment curriculum. Here it is. I know that this may on first inspection look chaotic to you. There's a lot of different things. But the reality is that this is actually extremely organized. It is extremely not chaotic. There may be a lot of different components, but if you look at this cell, there are various different compartments that allow you to do very specific jobs that are very defined. In fact, the whole concept of a cell defies the natural order of what scientists believe, and that, you know, it's spontaneous. Cells are not spontaneous. Cells do not obey this law of there should be more chaos. In fact, in order for you to keep this structure like a cell membrane and have the DNA in a very specific nucleus and have a transport system and have a mitochondria that is responsible for making energy, not making energy, but transferring energy from one form to another, that is not chaotic. That is actually a very, very well organized system. And just like my closet, if I want to have a well-organized closet system, what do I need to invest in order to keep this functional? It's the same concept. What do I need here to keep this thing together? Take a minute and answer that question. I'm waiting for you to answer that. And I'm bringing another picture in at the same time. Okay, I want to know what you need to invest in order to keep this organization system from collapsing. And then what do you do in order to make that happen? Excellent. Excellent. Audrey says you need energy. Dylan says you need ATP. You're 100% right. So what are you constantly doing? Sorry. What are you constantly doing in order to get that energy? Like, where does that energy come from? Okay, Scott's saying enthalpy, and I'm not disagreeing with you right now, Scott. Like, that is definitely part of this, but my question is even more basic than that. Like, you are constantly needing energy in order to keep these cells together, just like I am constantly needing energy to clean my closet. In fact, I am constantly battling the chaoticness and the randomness that exists in my closet. Your cells are constantly battling chaoticness and randomness inside of them, but the only way that they can do that is to use energy to clean. Where do they get the energy to clean that they need? Yes, Alexa says your food. You're 100% right. The reason why you eat, and it's not because you enjoy food, like, don't get me wrong, I thoroughly enjoy food, but you don't necessarily need to eat food that you enjoy eating. You need food in order to get the raw material of energy so you can keep fighting the constant battle of chaos that lives inside of every system that exists scientifically. Every system, whether it is a cell or it is a human body system or it is the human body overall, the human body is constantly heading into more chaos. Like, think about what goes on inside of your body. Like, it must seem so crazy chaotic in there, but the reality is there's a road system. It's your bloodstream. There is a pump that is responsible for pushing all the materials where it needs to go. It's your heart. Your nervous system is responsible for controlling and coordinating all the systems working together. You have a digestive system, which has a very different pH than the other systems that are outside in the body. If you didn't maintain that organization, well, you would head into massive chaos. And every single day, your body and your cells are heading into more chaos, but you are constantly eating to reorganize, to clean, to get the energy that you need in order to put your clothes back in the closet, metaphorically. But instead of putting clothes back in the closet, you're keeping the organization the same. We are constantly fighting entropy every single day in our lives. That is just a scientific fact. And every day that you live another day is a day where you win the battle against entropy. The day you die is the day that entropy wins, because you don't have enough energy to clean your closet and put stuff back where it belongs. The day that you die is the day that chaos wins and you cannot keep the organization of the cellular structure, or you have a breakdown of body systems that you cannot maintain because you cannot continue to fight the chaos. And the reality is that every single system in Earth will head into more chaos no matter what. As living organisms, we constantly fight the good fight, but at the end of the day, at the end of your life, entropy always wins. That is just the way of the world. The natural way is to always prefer more chaos. It doesn't mean that less chaos can't happen, because less chaotic things happen all of the time. Like, closets get cleaned. It can happen, you just have to invest energy. Cells can stay organized. It can happen, but you have to keep eating food in order to keep the organization. Body systems can stay organized, that's less chaotic, but in order for you to do that, you need to invest energy, which is the enthalpy component. These two factors play off of each other. Entropy is the chaos component. Enthalpy is the energy that you are going to need in order to fight the chaos. I'm going to stop and pause right now because I want you to give me the thumbs up that you are in a good place for entropy and what this means. And then I'm going to start talking about enthalpy. Take a minute, give me a heads up. Not a heads up, a thumbs up. Okay, a few more thumbs up. Let me know that we're in a good place. Otherwise, if you have questions, now would be a good time for you to ask me if you don't understand what entropy is about. Okay. So, let's talk about enthalpy. The symbol for enthalpy is actually delta H. So the way that I like to remember enthalpy, delta H, is that the symbol H is actually in the word. So when I think of enthalpy delta H, I'm just waiting for my highlighter to fire up, I think of the H in enthalpy. That doesn't exist here. Like, entropy is its own thing, that's S. Enthalpy with an H is the delta H. And any day now, highlighter, I'm just waiting for you. Enthalpy is something we've actually seen before, so let's highlight this H. Come on, buddy. Okay, this H and this H. Enthalpy is something we've actually seen before, this delta H, but I didn't call it by its actual name back in the day when we learned about it, only because I feel like when we saw delta H for the first time, it was in a diagram and it kind of probably would have overwhelmed you if I tried to give you the fancy scientific name for enthalpy. We saw delta H, and I'm going to just make this line skinnier. We saw delta H during a potential energy diagram. And the delta H, I don't know if you remember me running around the corner like a lunatic, which doesn't surprise any of you because that's kind of what happens every day. We looked at delta H and it was like, here's your house and here's the mall, artistic sketch of mall, which not to because you're all socially distant. Looks like a castle and that looks like an A, but here's your house and here's the mall. Do you remember the whole story of, does it matter if you take the Meadowbrook Parkway or I drive all the way out to Montauk to get to the Roosevelt Field Mall? Does the distance between your house and the mall ever change? And I don't know if you remember me running around like a lunatic and the two stools in between. That distance between the house and the mall never, ever, 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 ever changes. This, I don't want to go green. I want to go yellow. This is the delta H value. This is the same delta H value that we saw before. I'm not teaching you anything new right now. I'm just telling you that it has another name. The symbol that we used was delta H because that is the appropriate symbol. But it also has a fancy scientific name that we use as enthalpy. This particular diagram is exothermic. So I'm going to start typing over here. This particular diagram is exothermic. And the reason why this diagram is exothermic, it's massively large, is because it's going from high to low. So my notebook is being very slow tonight. Okay, exothermic, because it is going from high to low. And if we talk mathematical values, and this is calculated as final minus initial, this value should be a negative value. So exothermic, and I'm going to go underneath with this, and I'm going to go bulleted list just because it makes it a little bit more organized, a little less entropy. Okay, high to low, and it should have a negative delta H value. And I'm going to have to draw that. I think I can type a delta, can I? Today's not, can I go shape? Ooh, let's go shape. Oh, look at that. No, yes, yes, no, no, nope, does not want to play. Let's try one more time. Oh, there it is. Okay, so if we have an exothermic diagram, we have a negative delta H. Now, what you need to be aware of is that a negative delta H is going to mean that you are releasing energy. You are subtracting energy. You're going from high to low. And I want you to think about that whole concept that we were talking about earlier. Like, does the ball roll down a hill spontaneously? Does water flow down a hill spontaneously? Energy will always flow from high to low spontaneously or without any sort of external energy, because energy is being released during this process. You don't have to add energy. You don't have to absorb energy. In fact, you are releasing energy during this process, which means that is, you're not investing any sort of external energy. An exothermic process is always considered or is favored in nature because you're going from high to low. And the way I think of this, like if this is your ball at the top of the hill and you let this ball go, is this ball going to, hold on one second, Smart Notebook is not behaving. Is this ball going to roll down the hill spontaneously? It's going to go from high to low. That's just the way it's going to go. So let's compare this to a different diagram, which would be the opposite. Let's compare this to a endothermic diagram. So an endothermic diagram, I'm starting low, and this example of the ball is not the best example, but I'll fix that in a minute. Okay, Smart Notebook really does not want to behave tonight. So I'm going to apologize because this is taking longer than I wanted to. Okay, come on. It really doesn't want to behave tonight. Okay, alright, so we're going from low to high. And the way I think of this is if I'm going to go from low to high, well, the delta H here should be a positive value because in order for me to go from low to high, I have to absorb energy in order to make this happen. So I feel like I'm going to regret trying to change the color because this is taking forever. Okay, I'm going from low to high, and in this particular case, this really is not okay. I'm sorry. Smart Notebook is being very slow right now. Copy, paste. Okay. So in this particular diagram, this is not exothermic because I'm not going from high to low. In fact, this would be endothermic because I am going from low to high. And whenever I have to go from low to high, I have to absorb energy. So absorb or add, absorb during the process. Or another way that I like to think of this is I have to add energy from an external source. Like I gotta find energy from somewhere else in order to make this happen. And this is not favored in nature. And it would be the equivalent of, you know, me having to absorb energy in order to clean my closet. Like my closet's never going to clean itself on its own. My closet will stay in that chaotic random mess unless I come around and I turn around and I absorb, that closet absorbs energy from me in order to make that closet become clean and organized. An endothermic process is not spontaneous, or it's not favored in nature all by itself, because it would have to require some sort of external energy source in order to make that happen. So for whatever reason this does not want to copy. Let's try to clone. Ooh, look at that. Okay, I'm going to put this in here. And this would be something that's endothermic. So there are two factors here that are going to interplay off of each other. The first one is entropy and the second one's enthalpy. Enthalpy we've seen before, and it's that delta H value. If your delta H value is negative, that means that you are releasing energy out into the environment. And you know what? Like going from high to low, that's favored. Like I want you to think about, you are running and you're at the top of the hill and you have to go from high top of the hill to low top of the hill. Like, is that easier than going from the bottom of the hill down here and having to run up to the top of the hill? Like that's not favored. That's more difficult. You have to invest energy to run up a hill than to just let yourself just kind of like roll down the hill, which kind of happens when like I go running. Like I prefer to roll down hills and run up hills. And I don't know about you, but most people, you know, if given the choice between picking the easier thing to do, going from high to low versus low to high, this is always the favored thing in nature, going from high to low. And in exothermic delta H, we prefer to have a net delta H in order for you to be considered spontaneous. If you have a process that has more chaos and is also exothermic, then that would be something that is always, always, always considered spontaneous. So I'm going to take this information right here, over here, and I'm going to make a little summary list over here. And actually, while I'm making the summary list, okay. While I'm making the summary list, I just want you to either give me the thumbs up, give me the thumbs down, ask me some questions while I make this little summary table, and then we're going to call it a night because we're approaching the 45-minute mark, and I want to call it a night. So give me the thumbs up that we're in a good place, thumbs down if we're not in a good place, or ask me any questions that you have while I start to make this table. question, and it says there's no positive and negative. And then you said okay answered. I'm assuming that I either answered your question or you figured out what I was saying and connected it. So just Dylan, give me a thumbs up that you're in a good place too. Oh, you already gave me a thumbs up. We're good. Okay. So I don't understand why Smart Notebook really wants to give me a hard time tonight. It's very uncooperative. Okay, so something that is always spontaneous is definitely not how you spell spontaneous. So something that is always spontaneous. Shrink it down. Always spontaneous in terms of entropy and enthalpy. Well, something that's always spontaneous, and I go back to my closet, and my closet is never, ever, ever going to clean itself. So something that's always spontaneous will have a positive delta S. But that's not the only factor. Okay, not only do you want a positive delta S, you also want something that has a negative delta H. Okay, so that would always be considered spontaneous. And an example of something like this would be, you know, I think of, you know, you dropping a box of, I don't know, cookies, Cheerios. Like I'm thinking like in my house, like, you know, like the other day, like one of my kids spilled rice, and I'm picturing my kid dropping rice, you know, like a container of rice. When my son let go of the big giant thing of rice, the rice fell from high to low. That was an exothermic process because it was going from high to low. And when the rice was initially in the giant container, like it was organized. Like all of the rice was in the container. Well, guess what happened when the container of rice hit the floor in my kitchen? There was rice everywhere. There was more chaos amongst that rice because the rice was like all over my kitchen floor. It was underneath the table, like it was underneath the cabinets. Like I'm pretty sure like it went into cabinets because it just like things were open. The amount of chaos that went on there, that kind of process would always be considered spontaneous. So let's flip this and reverse this, and I'm going to go down here. Let's actually just copy, because this Smart Notebook. Smart Notebook. Okay, so let's copy and paste this in, and let's talk about things that are never, ever, ever spontaneous all by themselves. So okay, copy, paste. Okay, things that are never spontaneous. Things that are never spontaneous. So things that would never be spontaneous would be something that has a negative delta S, which means that there's less chaos. Like I think about my closet. Like my closet's never going to spontaneously clean itself. That is just not favored. And the reason why it would never ever clean itself is because I would have to invest energy, which is that delta H value. These two signs are going to be the exact opposite as soon as Smart Notebook wants to cooperate. There would be less chaos, and I would have to invest energy in order to make that happen. This is never spontaneous. Like it never just happens on its own. It can happen, and that's a whole other conversation. Well, how does it happen if it's never considered spontaneous? And it's like the whole concept in biology. Like I think about cells, like you're constantly fighting entropy, and you're doing that by investing energy. That is a whole concept for AP Bio, and how these two things work together. There's a whole other section of this called Gibbs free energy, and if we were in honors or AP, we would be talking about that, and we would be talking about a math value, and there's something called Gibbs free energy, how these two things are related to each other. And the entire beginning part of AP Bio is a whole discussion of, well, how do these two things interrelate with each other? The final thing I want to leave you with, and I'm not going to get into crazy detail with this, but it is worth talking about, very superficial, is that sometimes things can be spontaneous. They can be, but not always. Hold on. And I'm waiting for... Okay. So there's an area here called sometimes spontaneous. And the sometimes spontaneous category would be, well, what if one of these criteria is met? Like, more chaos is favorable, but I also need to invest energy at the same time. Like, would that happen on its own? Like, it depends. And then, well, what happens if I am releasing a whole lot of energy and, like, that's spontaneous? It's a lie. I am releasing a whole lot of energy, which in and of itself would be spontaneous. But, like, what happens if there's in that process? And this could be spontaneous too. It depends. And there's a sometimes moment. So the final thing I'm just going to have you guys, we're going to call this a night in about 2 minutes, is this question. Is ice melting spontaneous? Like, do you have to ask ice to melt? And I want you to think about that for a minute. Give me a yes or no. And kind of throw down here. Okay, Jordana says good, but can you please just give me answers from the multiple choice? Do you mean the ones from the review book, Jordana? I can pull them up for you in a minute. Okay, as soon as I finish this and we talk about ice melting, I will throw down really quick with some answers for you from the review. I'll pull them up. Answer this question for me: is ice melting spontaneous? Does ice just melt on its own? Okay, I have 3 no's here. Johnny's saying no. Jordana says yes. Alexa says no. This is a great question. So Scott, Brianna, Mason, Johnny, and Alexa, you're all saying no. And I guess my question is, well, when is it no? And Jordana said no, but yes, like, yes, it does not melt. Yes, it is spontaneous, but you need heat. Well, I feel like you absorbing heat is a really interesting thing because that technically is an endothermic process, which would be a positive delta H. So let's talk about that for a second. My question to you is, has it ever snowed before in your life? Like, if ice melting is not spontaneous, then shouldn't all the snow that ever have been snowed upon this earth still be here? You don't have to ask snow to melt. So, like, what is the critical point when snow decides it's time to melt? Audrey says it's spontaneous with a high temperature. Let's sketch this out for 1 second and then we call it a night. And Jordana, I will give you some answers. When you melt ice, melting is when you go from a solid to a liquid. So let's draw really quick. Here's what a solid looks like fixed, rigid geometric pattern. It's a terrible fixed, rigid geometric pattern. Okay, so here's solid versus here's liquid. Who has more chaos, the solid or the liquid? Okay, good. So this liquid is going to have more chaos. So for when you go from a solid to a liquid, this actually is a positive delta S, which means more chaos. That's favored. Yay! Like, this is good. Like, this is favored. However, melting. when you're melting, and this is your heating cooling curve from the beginning of the year, melting is when you go from a solid to a liquid, and directionality wise, you are going up the heating cooling curve. You are entering, which means that this is a positive delta H, and you have to absorb energy to make that happen. And in fact, absorbing energy is not favored. Like, that's just not cool. So you have two conflicting things here. Like, positive delta S is good. Like, yay, that makes a whole lot of sense. But then you got this positive delta H, which is like, no, like, I don't want to do that. That's not spontaneous. You have two things that do not agree with each other. There is one critical moment where the melting of ice is not spontaneous, but if you pass this moment, the melting of ice becomes spontaneous. And if I take a look at this side chat bar, Alexa hit the nail on the head when it gets warmer out. And in fact, there's a very, very, very specific point called the melting point, which is a temperature. Ice melting, is it spontaneous? The answer is yes. Yes. ... If you are above the melting point. But no ... if you are below the melting point. And this is where the Regents curriculum stops. Like, we don't go any further. If you were an honors or AP, you would then be doing some math here that would allow us to have a deeper conversation of, well, yes versus no, and there's something called the delta G value. We're not touching delta G with a 10-foot pole. All you need to know in this curriculum is things that are always spontaneous. This is always spontaneous. These set of conditions. You need to know never spontaneous. And then you need to know, well, sometimes there are things that are sometimes spontaneous. Sometimes because the two values don't necessarily agree with each other. And the fact or the point that tips the value, that point is a very, very specific temperature. And that's all you need to know for this moment. I'm not going to go any further with you. If we were in class, maybe we would have this conversation in more detail, but it's not worth having remotely because it's not in the Regents exam. Things are sometimes considered spontaneous. Smart notebook. These things are sometimes considered spontaneous depending on the temperature. And that is where we leave it. It's done. It's over. Give me some thumbs up to make sure that you understand that sometimes spontaneous component will depend on temperature. And while I'm waiting for you to give me thumbs up, thumbs down, or ask questions, Jordana, I'm going right now into my into the assignments page on the class website, and I'm going to give you some answers to the multiple choice. Okay. So, Jordana asked for some answers, so let's talk this out. Number 33, as the valve is open, so right now you have two separate systems. So you have an organized container of argon and an organized container of neon. When you open up this valve, the entropy or the chaos of this system is going to increase because they are allowed to mix. The right answer here for number 33 should be 3. Question number 34, which series of physical changes represents entropy increase? So I'm looking for more chaos, and the right answer should be 4. Solid has less, liquid has more, gas has the most. Number 3, so that's 4. 34 is 4. 35. Which tendencies favor a spontaneous reaction? Something that is spontaneous, I'm going to start with chaos. We should have more chaos. So I should be getting rid of answer choices 1 and 3. And then I'm going to start looking at the energy. Something that's spontaneous is going to have lower energy because you're lazy. Like, you don't want to invest energy if you don't have to. The right answer should be 3. Lie. The right answer should be 2. Lower energy and an increase in entropy. Question number 36, which will occur if the temperature of the system is increased? If you increase the temperature, there should be more chaos. More temperature, more movement. More movement is more chaotic. The right answer should be 2. Question number 37, you have a solid, which is like one giant thing, and then you are dissolving it in water. If you dissolve a solid into water, there is more movement, there is more randomness, there is more chaos. The right answer for 37 should be 2. 38, which change results in an increase in entropy? Like, I'm looking at the phases here, and I'm looking for a phase that is increasing entropy. The right answer should be 2 for 38. And for question 39, a reaction must be spontaneous. So I'm looking for the 2 criteria that make it spontaneous. I want something that is releasing energy, so that should be answer choices 3 and 4. But I also want something that makes more chaos, would be answer choice number 3. The right answer to 39 should be 3. Jordana, I gave you the answers. Just give me a thumbs up or ask me anything that you guys want me to explain on this little set of questions. Otherwise, I'm going to tell you where we're heading and what you should be expecting over the next couple of days. Give me thumbs up, thumbs down. Just make sure we're in a good place. And then we're going to call it a night. Okay. All right, so I think that's it for entropy and enthalpy and spontaneity. Otherwise, I think we're going to be calling it a night. There's nothing else I need to say to you. Good. All right, so just so you are aware of what's going to happen, Miss Chilton and I, we're going to be recording another ed puzzle on this concept of spontaneity. We're going to summarize really quick in like a minute or 2 video the concept of spontaneity. Entropy, enthalpy will give you a couple practice questions, and it's more of a review. And then what's going to happen is I'm going to be posting into the test wizard some questions that I will set a due date for, that I will ask, like, hey guys, like, the assignment's now in the test wizard, you have until this time to make it happen. And that's going to be what's happening tomorrow. I have nothing new really to go over with you. Tomorrow, if we were actually in class, I would say tomorrow would be a review. And then I probably would be testing this unit because we just finished everything equilibrium and kinetics. And if I was in a classroom right now, this would be the time and the place where like I would give you an exam. It's not happening right now. I'm going to give you a set of questions on spontaneity in the test wizard. And then what I may end up doing is I may give you a set of questions that would be kinetics and equilibrium combined. And it's more of like, hey, I want you to practice these questions and you complete it and you do the best you possibly can, just so I can see that you're understanding what went on here. If I open the test wizard, it'll tell me how long something took you. So if you did 40 questions in 30 seconds, like, it's clear as day you didn't give me your best effort. But I will come up with how I'm going to handle some sort of, I don't want to use the word assessment because that implies that I'm grading it. It's going into your grade. Your average is a grade, which is not something that anyone has told me what's going on with that at this time, but more of just a check for myself, a check for understanding, to make sure you understood what happened over the course of this remote learning time. So I'm gonna call it a night. I think we're in a really good place, and I will shoot you a text in the remind when the ed puzzle is ready, when test wizard is up and running, and then I need to game plan where we're going next because we are heading into another brand new unit. So have a wonderful night. I miss every single one of you, and I will touch base with you soon. I do not plan on streaming tomorrow because I'm going to give you the review questions to be working on in ed puzzle and test wizard. We'll most likely be heading into new material on Wednesday, which means my next stream for you probably will be on Thursday on whatever it is that we're talking about. I will see you all virtually soon. Have a wonderful night.